my name is Ben Farm. I work on gravitational waves, and particularly I work on data analysis for a project called LIGO, which is the Laser Interferometr Gravitational Wave Observatory. We are an international collaboration that is searching for these elusive gravitational waves that I'm going to tell you more about today. So this is going to be a bit of a change in topic from the mainly neutron stars that I hear you guys have been learning about for the last several weeks. So there are definitely some neutron stars involved in this talk, but we'll also branch out to black holes and more specifically gravitational waves. All right, so you I think have already heard about general relativity. Already know about how it works. In a very basic sense, it's just a geometric way to think about gravity. And massive things cause curvature, and other things feel that curvature, and it affects how they move. Now we're going to take that up one step and add in when these bodies are accelerating, not only do they feel this curvature in space-time, they cause curvature themselves and cause ripples to travel out, which are these gravitational waves we're looking for. So this talk is going to focus on gravitational waves from three very specific kinds of systems that all fall under the class of compact binaries. So you've heard a lot about neutron stars, which are one type of compact object. Black holes are obviously another kind of compact object, and then also white dwarfs are commonly called compact objects as well, but I won't talk about those at all because we are not sensitive to those with LIGO. So the kinds of compact binary systems we're going to be looking for are binary neutron star systems composed of two neutron stars, neutron star black hole systems where you have a neutron star and a black hole orbiting together, and finally binary black hole systems where we have two black holes orbiting around one another. And specifically, we're going to look at stellar mass, what we call stellar mass black holes that are close to the mass of our sun, about 5 to 10 times the mass of our sun. So when you get these systems orbiting around one another, think of the solar system. You have objects that are orbiting around one another, and the motion is very, very stable. The Earth hasn't really gone anywhere in its orbit besides around it for many, 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 many years. Compact binary systems are a little bit different. As they orbit each other, as I said, they emit this gravitational radiation, and this gravitational radiation has sizable energy content in it. And when you take energy out of an orbit, then you cause the orbit to shrink and get these things closer and closer together. So this is a numerical simulation where Einstein's equations of general relativity are solved on the fly, each step of this simulation. At the very center here are two black holes orbiting one another. And on the outside here, you see a projection of what the gravitational radiation, what the stretching and squeezing of space-time looks like from these things. And as they emit all of these gravitational waves, all of this radiation and energy out of their orbit, they're caused to get closer and closer together, making the gravitational waves get stronger and stronger, until eventually these two black holes touch and merge and give off a big burst of gravitational radiation, and then finally settle down into a nice steady black hole. So waves, I've been talking about the stretching and squeezing of space-time, but what does that actually mean? How can we measure that? Up here is shown a ring of particles that are freely floating in space. So you can imagine like asteroids and the asteroid belt or something. And as the gravitational wave travels through these freely floating particles, it stretches and squeezes the space-time in an oscillating fashion. It actually causes the distance between these objects to grow and to shrink. And it causes this oscillation, which is characteristic of gravitational waves, and that's what we're looking for. Now, the stretching and squeezing of space-time, though, is incredibly tiny. This is a very, very exaggerated animation I gave here. So the strain, which is just a change in length over the length that we're measuring, so that would be like the diameter of this circle here, is incredibly tiny, 10 to the minus 23. To give you just it's not even fathomable to the human mind, I think, but to give you an idea of what kind of scale we're talking about, if you were to measure the distance between the sun and our nearest star, Alpha Centauri, which is over 4 light years away, that's corresponding to measuring that distance over 4 light years down to the precision smaller than the width of a red blood cell. So it's incredibly tiny measurements. So this is it's just amazing that this is even possible. So how do we make such tiny measurements? We use a very, very excellent feature of light called interference. If you have two light waves passing by one another, if they have exactly the same wavelength, then the peak of each light ray lines up with the other peak of the light ray, then you get really bright light out. And this is how lasers work, for example. They emit very, very coherent light where all the peaks line up with all the peaks and all the troughs line up with all the troughs. If you have these two light rays get slightly out of phase with one another, and you start to have peaks line up with troughs of the other waves, then you can get them completely canceling out and get all of the light is just gone out of the system. And so you can use this to make very, very sensitive measurements. These destructive interference is what they call it when it's completely dead, and that's, for example, how noise canceling headphones work. The way we make use of this is with lasers that emit very coherent light, and we split it in what's called an interferometr. So we take that very coherent laser light, we throw it through a beam splitter that splits this beam in half, and it sends light down one arm, half of the light down one arm, and half of the light down the other arm. It travels through this, usually held in vacuum to remove noise effects. It bounces off from mirrors at the ends of the interferometer arms. It comes back and is collected into one single beam again. And if the light was in phase going in and the arms are exactly the same length, then the light coming out is still coherent and bright, and we get a nice bright spot at the end of the interferometer. If the arms of the detector slightly vary, then we can get slight changes in length of one arm versus the other that causes the light to be no longer coherent when it comes back to the detector, and we see dimming of the light. And so just by monitoring the intensity of this light beam coming out, we can make very, very, very sensitive measurements of the relative lengths of these arms. So I should say, please feel free to interrupt at any point to ask questions. If we start getting a little bit short on time, then maybe I'll, at some point, save questions for the end. But feel free to ask questions if you have any as we go along. Yes?
So in quantum mechanics, each individual photon interferes with itself.
Mm-hmm.
Is that what's happening here, or are you using the beam as a whole as the interfering wave?
So we're actually using the beam as a whole. And there's actually, in LIGO, we added 2 more mirrors in here to make what we call Fabry-Perot cavities. And the light actually bounces back and forth in the arm about 200 times before it leaves the detector. And so we use the entire coherent state of the light to make measurements. And so
that means it's a strictly classical analysis.
Well, it's very much non-classical because in the end we get we have such precise measurement of the position of these mirrors, for example, that these big macroscopic tens of kilogram mirrors are measured as a quantum body, and quantum noise, and specifically fluctuations in the surface of the mirror, is a very big noise source for us. But the details of the laser light's quantum state, I'm actually not as up to date on. Yes?
How long are the arms?
I will get to that in a second. So, we take what is typically a tabletop experiment, interferometer, microsync interferometer, and we scale it up and we put it in the desert. And we make those arms 4 kilometers long. So that's about 2.5 miles. And I remind you that these are big vacuum tubes, the biggest vacuum on Earth created for the sake of this interferometer to make us very, very sensitive. So coming out of this detector, we get this, to the first degree, we get this brightness of a laser light, and we monitor the brightness of that laser light very well. And out of that, we can extract the waveform that's passing through. The gravitational wave is passing through our detector. This is what an example signal looks like from a compact binary merger. And if you listen, we can convert this vibration of space and time into something that we can actually hear. The frequencies are actually in the audible range. We turn it into sound and have a listen. So there's actually a long time spent at very low frequencies that these speakers aren't able to reproduce. But what's happening there is a compact binary is orbiting, the 2 black holes are orbiting around one another at very far distances, which the frequency of this wave corresponds to the frequency of the orbit. So they're orbiting very far apart. You have a very low frequency wave. Gravitational radiation causes these bodies to get closer and closer together. The frequency goes up, and then it starts to run away, and it gets higher and higher and higher, and you get this chirp-like signal that comes out. So that's just a nice signal. I wish that we could measure things like that with LIGO, but we don't, and that's why I have a job. So the noise that we have to deal with when we're measuring changes on 10 to the minus 23 kind of sensitivity. So over the 4 kilometer long arms that I said we have in our interferometer, that's changes in length that are smaller than 1/1000th the width of the nucleus of an atom. So you can imagine how many noise sources we have to deal with, and the detector does not quite sound like that when a signal goes through it. So this is the noise that we have to deal with. This is just a very, very Gaussian noise. And you'll notice it's not quite white. it's got some extra low frequency components on the red side. It's got some extra high frequency components. And that comes from, on the low end, on the low frequency, our noise is completely dominated by seismic activity around the detectors. And then on the high frequency, it's dominated by shock noise, and basically counting photons and how we're uncertain about how we do that. So, I showed you signal, and I showed you noise. We can now look at signal plus noise. And just by eye, I think you can probably tell where the gravitational wave is here. For fun, we can listen. Alright, so that was pretty easy, right? That's a signal to noise ratio of 500. If we measured that, then I would be very nervous about where our local environment looks like in the universe. So there's the signal that's in the noise. Now, if you take this down by a factor of 10 and look at a signal to noise ratio of 50, that starts to get hard to pick out by eye, just looking at the strain time series. If we listen, our ears are a bit better at this analysis than our eyes are. Okay, so that's a signal to noise ratio of 50. That's still, so if we had a signal to noise ratio of 50 signal go through, we would also be very nervous because we should have detected tons and tons of gravitational waves by now, and we haven't. So now we can take it down by another factor of 10 to a signal to noise ratio of about 5. And this is about where the threshold is of our detection abilities with our current analyses. Anybody here? No. It's in there, I promise. So that's what the signal looks like. And this is like what I like to call job security. This is why I have a job. It's not an easy problem. And you can't just sit at the detectors with headphones on and try to pick out these signals. So we need to be very clever about how we do this. So just to go into detail about a few of the noise sources we have to deal with. So we have this very Gaussian-like noise that you just heard, but on top of that we have the added problem of these very short duration noise transients that happen that are very non-Gaussian. And they pop up all the time. We don't always know what they are, but they will also often have very similar shapes, so we can actually classify them into categories. On the top left here, so this is showing, these are all time frequency plots. They're spectrograms where the x-axis is time and the y-axis is frequency. And so higher things are higher frequencies in the y scale. On the top left here, this shows what they call a magnetic glitch. And so this is the channel that we actually look for gravitational waves in. In the top right of some of these plots are environment channels that we monitor to have a sense of the data quality of the gravitational wave channel that we're looking at. So this is showing the magnetic field has a huge spike at one of the detectors, and this is how it transfers to the gravitational wave channel. So that's something that is not a gravitational wave source, but may look like it to our analyses. In the middle here shows scattered light from the lasers. So sometimes the light bouncing off of these mirrors will get scattered into the vacuum cavity and bounce all around, and you get these really weird arch-looking things that we often see. On the top right is just the temperature, the thermal control systems fluctuations, so trying to compensate for the heating of the mirrors from the laser light. Those control systems can sometimes have glitches in them, and that transfers to the gravitational wave channel. On the bottom left here is an airplane going over a detector, and so on the top right of that plot is a microphone channel, so that's recording the sound of the airplane well above the detector, and it actually, just the plane flying over the detector at 30,000 feet can cause very, very big glitches in our detectors. So there's a couple of others here. I don't think they're as interesting. Here's a seismic glitch, which is just seismic activity near the detectors. That's the seismometer that recorded it there. Now, when I say seismic activity, I don't mean like sizable earthquakes that you could feel from the ground. I mean magnitude 4 earthquake in New Zealand just can completely knock our laser out of block in the U.S. So there's some of they are the most accurate seismometers on the planet, and it's a problem because we don't want to measure seismic oscillations. We want to measure gravitational waves. So with all of these noise sources, it makes pulling out these very, very quiet gravitational wave signals out of the data a very tough problem. So beyond just making really good data analysis software, we also have multiple detectors around the globe to try to isolate the noise sources. We have one detector, so LIGO is composed of two detectors, one in Hanford, Washington, and the other in Livingston, Louisiana. So they're separated across the continental U.S. pretty well. And then we collaborate with a third detector near Pisa, Italy. And that's a slightly smaller detector. Those arms are 3 kilometers long each. And so we take data simultaneously from all three of these detectors around the globe. And the hope is that airplane flying over Hanford, Washington won't align perfectly with some seismic activity over in Pisa. Obviously that does happen sometimes, so we still need to be very careful about how we analyze our data. But by taking data from three very separate detectors around the globe and monitoring all of these data channels, there's 99% of the data we take in LIGO is actually environmental channel. Only 1% is the gravitational wave stream. We can be fairly robust against these noise sources. Yes?
Are there any plans for ability to do this in space?
Yes, I'm very glad you asked. There's a project called LISA, which is the space-based version of LIGO. And it was ranked very, very highly for many, many years. I think it made it like second or third in the decadal survey that they do of deciding which are the most important missions for NASA to do in the coming decade. But it didn't rank highly enough to get funded, and so the funding has dropped back a lot. And there's actually a lot of astronomers that have worked for a very long time on simulating what LISA can do and figuring out how to solve the data analysis problem. So they have a very, very different problem than we do on the ground. Obviously, they have a much cleaner signal. They remove all that seismic noise and everything from their data. And their noise source is actually other gravitational wave sources that they're not interested in. So there's an entire background of gravitational wave noise if you go to space from white dwarf binaries in the Milky Way. And that just looks like noise in the data. And so they have to be able to disentangle all these gravitational waves on top of one another. So it's a very interesting problem, and it's very, very different. I wish we had that problem in LIGO. Another question?
What was the basis of the 4-kilometer length?
So the 4-kilometer length put us at the sweet spot for our sensitivity in terms of the frequencies of gravitational waves we're sensitive to. Our noise, if you look at our noise floor in the frequency domain, it's, like I said, it's dominated at the low frequencies by seismic noise and shock noise, Compton photons at the high frequencies. So we have this window in frequency space that we're sensitive to. And by having 4-kilometer long arms, that puts us at right the frequencies where we expect binary neutron stars and black holes to be colliding at. So it's sensitive to just the very final stages of this merger process of compact binaries. That's why we picked that length. So to first lay down some of the things that we can do with LIGO, I'll go over what we know about compact objects so far, very, very briefly. So you've learned a lot about neutron stars, and you've probably heard a lot of this from Dr. McCann already, but we've detected binary neutron star systems, and that's what, for example, has shown indirectly that gravitational waves exist. We've seen the in-spiral, the Killer pulsar system in exactly the way that we would expect if we're emitting gravitational waves and losing energy from the orbit in that way. There's a second pulsar system, J16142230, and that has given us a very, very accurate measurement of the maximum mass that we've seen so far for neutron stars. So that pins one of the neutron stars at about 1.96 solar masses, and that is the tightest constraint on the high mass side that we have of neutron stars so far. That's a very, very important measurement because that gives us information about the equation of state of neutron stars, so how the pressure relates to the density of these things. And we believe we've detected lots and lots of gamma ray bursts, these very, very short duration, high energy bursts of gamma rays from around the universe. And we believe, so there's two classes of gamma ray bursts. There's short gamma ray bursts and long gamma ray bursts, named because of the duration of the gamma ray burst. The short gamma ray bursts, many think are from binary neutron star mergers. But we still don't know. We haven't been able to tie this unquestionably to the binary neutron star sources. And so far we've measured about 10 binary neutron star systems in the universe. So this is showing some of the theorized equations of state for neutron stars that we've had so far, and how the astronomical measurements we've made so far constrain which equations of state seem to be more realistic than others. On the x-axis shows the radius of a neutron star, and on the y-axis its mass. And these lines show if this theoretical equation of state were true, what the mass-radius relation would be for that neutron star. And in the top here is that very, very tight constraint on the maximum mass of a neutron star that I mentioned, and that rules out basically anything that goes above it. It rules that out as a possible equation of state. So this is really just this one measurement of this one system has taught us a lot about the equations of state of neutron stars and how matter acts at very, very, very high densities. So our current constraints on black holes come from much tougher measurements. So the no-hair theorem says that black holes can be completely described by the mass, the spin, and the charge of the black hole. Everything else about the black hole's history has no effect on the end state of the black hole. We've detected, we think, black holes through observations of accretion disks around them. So because black holes are black, we can't see them with light directly, but we can see matter around them that gets heated up as it's falling into the black hole. So that's that's basically where we've learned everything about black holes so far, is by watching the matter emit light as it goes around the black hole. So this is a diagram of the black holes measured to date, along with the accretion disks that we think they have. Some of the first scale here is the Sun-Mercury system. So you can see we've measured all kinds of systems with very, very massive stellar companions and very, very small stellar companions and very big accretion disks, very little accretion disks. And by having very, very good models for what the emission from these accretion disks looks like, that's how we can make inferences about black hole properties, black hole mass, black hole spin. Specifically, black hole spin is a very tough problem that we hope to solve with LIGO. So the way we've measured black hole spin to date is by making, like I said, very accurate models for what the emission from the accretion disk looks like. The spin of the black hole decides what the innermost stable circular orbit of objects falling into the black hole can have. So as matter settles down into this accretion disk and is falling into the black hole, it makes very, very slow inward motion toward the black hole until it hits this radius of innermost stable circular orbit, and then the orbit changes characteristics and goes into a plunge into the black hole. And so that's right where the accretion disk cuts off, and that gives us a very hard edge for the inner part of this accretion disk, and a very, very strong feature we can look for in the emission. And so there's two techniques that are used to model the emission from this accretion disk, and it parameterizes this innermost stable circular orbit and uses that to back out what the spin of this black hole might be. So those are continuum fitting methods, and a second method, the iron K alpha, which looks for a very specific emission line from iron, and tries to find that in the spectrum from the accretion disk. Now, both of these methods are very difficult to extract measurements from it. It requires a lot of very, very precise modeling of what the emission of these things look like. Not just the exact radiation from the accretion disk, but modeling how those light rays are worked around by the black hole and all the paths that they take to get to our telescopes. And so it's very, very tough measurements to make. And where these two methods have been able to be applied to the same problem, they don't always agree. So that kind of raises a bit of doubt about the measurements of black hole spins that have been made to date. So how can gravitational waves help? This is showing a simple model for what a gravitational wave from a binary black hole merger might look like for 3 different spins of the black hole. So that's a dimensionless spin parameter between 0 and 1 is the full possible range for black holes to have according to general relativity. And this shows what varying the spin from 0 all the way up to 0.6 can do to the gravitational wave. So that the information about the spin of the black hole is imprinted in these gravitational waves if we can detect them and characterize them properly. The problem is that it's a very, very hard thing to do. So I've said that continuum fitting methods and iron K alpha methods for measuring spin from accretion disk emissions is tough. Modeling these gravitational wave sources isn't very easy either. This is showing the one very simplified model for what the emission from a binary black hole would look like in gravitational waves, using what's called post-Newtonian expansions to approximate. And there's a lot of stuff in here. There's a lot of parameters, and this is just a simplified model that we actually can't even use to do the characterization of these sources because it's not precise enough. So in these gravitational waves, I said the spin of the black hole is imprinted. There's also information about the orientation of the spin axis of each of the compact objects. And the reason that is there's spin-orbit coupling that passes angular momentum between the black holes and the orbit itself. And it causes precession of the binary orbit from our line of sight. And so here is a simulated neutron star black hole system. On the left, I'm showing an orbit over here. On the right, I show the spin vectors of the black holes in red and blue, and the black is the orbital momentum as it's precessing around, and then on the bottom is the gravitational wave this thing would emit. And so you can see all of this precession going on, and that precession causes modulation in the amplitude of the gravitational wave. And it also causes changes in the phase that are harder to tell by eye. And then again, for a binary black hole system where both things have a measurable spin, you'll see two very noticeable spin vectors over here that play with the angular momentum of the orbit. And so all of the variables that go into defining this binary system, all of it is richly imprinted in this gravitational wave that we can detect it. So that's why we hope to learn a lot about these compact objects and gravitational waves in a way that's very different from how we've learned about them so far with electromagnetic light. So how those gravitational waves I was showing were how it's emitted from the system itself. The separate problem is projecting that gravitational wave across our network of detectors. And that's how we would obviously measure these things and extract information from them. Our detectors aren't like telescopes. We can't point them at some spot in the sky and look for gravitational waves. They're more like microphones. They're omnidirectional, and they're sensitive to gravitational waves from all over the universe. They're not equally sensitive in all directions. This is showing the antenna pattern for a ground-based gravitational wave detector. It's kind of peanut-shaped. We're very sensitive above and below the detectors, and we're less sensitive in the plane of the detector. And so if we just had one single detector, besides the problem of detecting a gravitational wave and the noise in the first place, we'd also have a very hard time localizing that gravitational wave from just the one detector. The location information is slightly imprinted in the amplitude of the gravitational wave, because if it's the same exact source were directly above us, the signal would be louder than if it were in the plane of the detector. But that information is degenerate with things like the distance. If you move that compact binary further away, obviously the source gets quieter. And so we can't use the loudness of this signal to figure out where it came from in the sky with just one detector. So that is another reason why we have more than two detectors. Well, we originally had two, just as Virgo joined our network. And from the three omnidirectional detectors, using the time of arrival as the gravitational wave passes through the Earth and it brings off in all of our detectors, we can use the time information to figure out where the source came from in the sky. So if we have just two detectors online, so Virgo, we're offline, from two gravitational wave detectors, both detecting the same system, we can constrain that source to a ring on the sky. And that ring is slightly broken up because some of the spots in the ring are a little bit less likely than others based on how the orbit would have to be oriented to our line of sight. But from two detectors, we get basically a big ring in the sky. By adding a third detector, we can often constrain it to being two big blobs in the sky, basically on either side of the three detector plane that's formed from the detectors. So this makes detecting these things easier, having multiple detectors in our network. It also makes localizing them on the sky much more tangible and easy to pass information off to electromagnetic observers to try to do what we call multi-messenger astronomy. So this is, what I showed before was the sky location that we would constrain for one single source. This is showing all of the sky localizations of the population of sources that we may detect on the sky. And you'll notice that a lot of these things are concentrated over these two patches in the map. Anyone have a guess as to why they're all concentrated in one specific area? So this is on top of the map I showed previously. So this is on the of the Earth. You'll notice that up in here is North America. This is where our two LIGO detectors are. So we have two detectors who are most sensitive directly above them in the same part of the globe. And so we detect the most sources right over the U.S. and below the U.S. on the opposite side of the globe. And then we added a third detector. Because that third detector only has 3-kilometer long arms, it's less sensitive than the LIGO detectors. So it actually doesn't add to our detection ability by that much. We don't have that much more sensitivity in terms of the sources we can detect, but it does help us localize these things in the sky better. So along with these two parameters, the location, the RA and dec in the sky, we get 13 more parameters that we need to completely define the binary system. And that goes from the masses of the two compact objects, their spin magnitudes, the orientation of the spin of these two compact objects, the time and phase that they enter the sensitivity bandwidth of our detector, distance, the inclination of the binary, all that information is imprinted on the gravitational waves. And it's our job to try to extract all that information to actually perform gravitational wave astronomy, which is what we want to do. So I've mentioned multi-messenger astronomy. The goal of multi-messenger astronomy is to connect two completely separate spectrum to make measurements about astronomical objects. So multi-messenger astronomy so far has been really confined to electromagnetic spectrum, along with neutrinos, which are very high energy particles. Gravitational waves, we hope, will play a very, very key role in multi-messenger astronomy, and we can measure things in gravitational waves, find them, localize them in the sky, and then tell electromagnetic observers where to point their telescopes to try to find electromagnetic counterparts to these types of sources. So on the bottom of this, so I have this time bar here, and the time is on a large scale. On the top show the possible electromagnetic counterparts we may expect for these gravitational wave sources. So on the very short time scales, we have these gamma ray bursts that I had mentioned. Those operate on very, very, very small scales, I mean on seconds of time scale. Next, after that gamma ray burst, we have the afterglows from these gamma ray bursts, which I'll talk about more in a bit. On even later timescales, on the timescales of days, we have Kilonovae signatures that may exist. And these are still very much theoretical. We think we may have detected one, but LIGO will help us find more of these, we hope. And then finally, the radio signal of the afterglow on more a month's timescales. On the bottom of this time axis shows the timescales for our actual detection and characterization of gravitational wave sources. So it's not just a one-step procedure where we detect and localize this gravitational wave source in the sky. In seconds, we can actually detect the thing using our detection pipelines. The detection pipelines work by constructing before the analysis a big bank of what these signals may look like, a big template bank, and then applying that template bank to the data as it rolls in from the detectors, and trying to find where there happens to be some time in the data that rings off with a template that's in our bank. So that detects the signal. That only tells us a time at each of the detectors. From just the time that it happens to ring off with our template, we can do some very basic sky localization and try to find the source on the sky. That kind of map is generated here. So this shows what just using that time information on a very, very quick time scale, like maybe on a time scale of a minute or two, we can localize the source in the sky to this ring. And then the job of fully modeling the source and really, really strongly characterizing the mass, the spin, all of the other parameters, along with the sky position, gives us a much better estimate of where in the sky the source came from. And that kind of map is over here. So you see we ruled out most of this ring and localized it to just a few blobs along it, which would be much easier to follow up than the 1,000 square degrees that a very rapid localization gets us. So in order to do that, though, we need to fully model the data to come from the detector for any possible gravitational wave source that we could be seeing. And that process is very, very costly, computationally speaking, and that can take days to even a month to do. And so to find most of these sources, that's way too long of a time scale. So we need to get faster if we really want to localize precisely on the sky, fast enough for it to be useful for electromagnetic observers. And so that's the problem that I work on particularly. So I mentioned gamma ray bursts quite a few times. The actual mechanics of the emission from a gamma ray burst is we think it's from a binary neutron star merger for these short gamma ray bursts. What happens is you have these two neutron stars collide together, all this matter is flying around, the black hole is formed in the very middle, and that black hole, as it accretes this matter, launches these very ultra-relativistic jets that smash into the interstellar medium around it. So on the very short time scales, you just get this very big burst of gamma rays, this very, very narrow emission. So there's a jet of gamma ray burst emission, we think, that launches into the interstellar jet, right? Interstellar medium. Now that jet, we only get to see if we happen to be down the barrel of the gamma ray burst. And so that makes it very unlikely for any given gamma ray burst to be detectable on Earth, because we are probably outside of that jet, outside of that lighthouse, as it emits all these gamma rays. For that reason, we tend to only find gamma ray bursts that are very, very far away, because there's most of these sources are far away. As you go further out, you get more and more volume, and you get more and more chance to see a gamma ray burst. And so most of the gamma ray bursts we've detected to date are very far away, way too far for us to be able to detect the gravitational wave emission from them. But as that jet, that ultra-relativistic jet, smashes into the interstellar medium, it has a shock wave that slows down all the matter as it's going into the interstellar medium, and the radiation slowly loses energy. It starts off in the X-rays, very high energy, and then as it slows down, it emits at longer and longer wavelengths, entering optical and eventually hitting radio. So that's why the time scales for the afterglows were much shorter for the optical and X-ray emission than for the radio emission. Yes?
Is it possible to make those levels clearer? I can't read that.
Yeah, I'm sorry, the projector is not quite rendering them as well, and I should have made the letters bigger, but the actual details that are, so I could say in words what they are. Down here is showing the low energy gamma rays that first come out of the black hole central engine. And then we have this very fast shell that's hitting into the interstellar medium, and then as it goes out, it slows down and slows down further, and the emission starts to get longer and longer wavelengths. And the emission, the source of the emission, this shock as it's going into the interstellar medium grows, and emission becomes more and more spherical as time goes on. So even if we don't happen to be looking down the barrel of the initial gamma ray emission, that emission, the afterglow emission, as time goes on, gets more and more broad. And so we actually have a chance of measuring afterglow emission at late times, even if we didn't see the gamma ray emission. And that's where we hope LIGO will really come into play. We're sensitive to the gravitational waves coming from this source, no matter where we happen to be oriented with the system. So we can see the gravitational waves coming from the very side of the orbit. So we can tell astronomers to point telescopes at a specific region of the sky and look for this afterglow emission as it becomes more and more isotropic. And so that's one way that we hope to really connect the gravitational wave and electromagnetic spectra.
Why would the emission for some of those lines straight and others wiggly?
Over here. The purple are the gamma rays. They're very, very short wavelengths, and so that as we go to X-rays, to visible light, and to radio, the wavelengths get longer and longer, and the wiggles just get drawn out. Does that answer your question? All right, so that's the gamma ray and afterglow mechanism. I've also mentioned kilonovae. And so kilonovae are something that were theorized for some time before we had any hope of detecting them. Kilonovae are from the same mechanism, the same kind of binary mergers, but it's more of an isotropic emission than this very, very beamed gamma ray burst that I was talking about earlier. And so the mechanism here for the emission is not this very, very high energy particles hitting into the interstellar medium. It's the matter that's left around after the merger of these binary neutron stars forming, coming together and forming very high mass particles. And that nucleosynthesis going on emits very isotropic radiation, albeit very dim radiation. So it's something that we don't think we're very good at detecting just at looking everywhere in the sky at once. We think that we can measure these things if we know where to look with telescopes. Specifically, this emission is really in the optical and infrared. And so we think that we can actually detect this type of emission if we know where to look, and that's where LIGO comes in. If we can tell astronomers to look at this part of the sky for this very specific kilonova signature that will last on the order of days, then maybe we can detect these things. So to date, there's only been one possible detection of kilonovae. This is showing data taken by the Hubble Space Telescope. There was a gamma ray burst that was very close by, surprisingly close by as far as gamma ray bursts tend to go. And somebody had some extra time on Hubble to look at a source for, they had a very specific proposal in to try to find the kilonova signatures. And this gamma ray burst really gave them the first opportunity to look close by where the signature from the kilonova would actually be bright enough to have a hope of seeing. And they saw a slight brightness. And so this is the strongest evidence that we have that kilonovas actually happen to date, but it's still very, very sketchy measurement, and we hope to find lots more of these with LIGO as we go on. So I talked a lot about LIGO. I haven't really said how long we've been observing and when we hope to measure gravitational waves for the first time. The detectors were first constructed in the 90s, and you can imagine going to a funding agency and telling them that you want to measure changes in length along 4 kilometers that are smaller than 1/1000th of the nucleus of an atom. They tend not to take you too seriously. There was a whole lot of technology that needed to be proven to make that sensitive of a measurement. And so the time scale for LIGO to get to its full design sensitivity was purposefully done in an iterative way, where we first built what we called initial LIGO that was much less sensitive than what we wanted out of our final detectors, but we could actually prove a lot of this technology existed and worked to make these sensitive measurements. And then we would take data from these detectors as we made them more and more sensitive, and maybe we'll actually get lucky and detect some gravitational waves, but we don't really expect to measure gravitational waves until we get to design sensitivity. So in 2010, the detector shut down from their initial configuration, and we spent the last 5 years upgrading them. We're basically ripping out most of the major components and replacing them with better parts. So some of the most important ones are like the seismic isolation tables that isolate all the optics and the laser from seismic activity. But there's loads and loads of other advancements that we've been installing. And in September, we come online with what we call the advanced detectors, which are the start of reaching design sensitivity. And so by 2019 is when we expect to get to full design sensitivity. And to give you an idea compared to initial LIGO, that'll be about a factor of 10 more sensitive. So we'll be sensitive to a factor of 1,000 more sources. And we hope that gravitational wave detection will actually be routine, which is a very exciting idea. So this is showing the volume that advanced LIGO will be sensitive to in the local universe compared to initial LIGO. And so the amount of sources that are going to be possible in this advanced LIGO sensitivity volume are huge, and we really are very excited for the upcoming advanced detector era.
How big is light years, that radius?
In light years, off the top of my head, I don't know. In terms of megaparsecs, we are sensitive. It depends on the type of source. Binary neutron stars tend to be much quieter in gravitational radiation. We'll detect those out to about 200 megaparsecs with advanced LIGO. Binary black hole measurements binary black holes are much louder, and they'll reach out to about a gigaparsec in terms of distance for binary black holes.
I think your logo at the top says 100, little bar says 100 million light years.
100 million light years, yeah, that little bar up there is 100 million light years. Thank you, that's the scale for the time. Yes. All right, so here's the roadmap. This is showing the sensitivity of our detectors over the next few years as we turn them on and reach more and more closer to our design sensitivity. In 2015, this year, in September, we hope to come online with a sensitivity around this range right here. And then we take our first science run that'll be about 3 months long in the fall of this year, reaching into the winter. And then we will shut the detectors down again, do some minor advancements in some of the technology, and then come back online for our second observing run in 2016, which expects to see the sensitivity around this green area here. And then we'll take the detectors offline again, do some more tweaking, and come back online in late 2017 to reach this red curve. And then finally, around 2019, we hope to reach full design sensitivity. So this is for the LIGO detectors. The Virgo detector is a similar progression of sensitivity, but on a slightly delayed timescale. They don't expect to come online until sometime probably late next year. So the first few observing runs of LIGO are probably only going to be 2 detectors, and that makes the whole multi-messenger goal a bit more difficult, but they do plan on coming online at a slightly delayed time and adding it to our network. So how this compares to what we expect for event rates. The event rates for for binary neutron star mergers, neutron star black hole, and binary black hole mergers are very, very uncertain, just because they're so hard to detect with electromagnetic telescopes. So we don't have great constraints on the formation channels for these things. So the event rates estimates are orders of magnitude uncertain. In 2015, when we operate for just 3 months, we expect anywhere from 0.004 binary neutron star mergers to 3 just over the duration of those 3 months. And so that, to give you a scale for how sensitive it is about a factor of 4 more sensitive than the last version of LIGO that turned off in 2010. When we start our second observing run in 2016, that goes up to as many as 20 binary neutron star detections in a year, or as low as 0.006, going all the way until 2019 with the network that I talked about today. And that goes as pessimistically as 0.2 detections per year. So we may need to go as many as 5 years to have a binary neutron star detection. That low of an event rate is very, very pessimistic, and the very, very optimistic is more than 200 range. Likely will be somewhere in the middle there, but there's very, very, very heated debates from both sides, the pessimistic and optimistic theorists, on what event rates we should expect for LIGO, but we don't really know until we look. So exciting times are ahead, and hopefully over the next few years, gravitational wave astronomy is going to become something that the public is very, very familiar with, and we hope to really contribute to electromagnetic observing and neutrino observing in the coming years. Thank you. I hope you have lots of questions. Yes? for how the detectors actually work. So the interferometer that I showed before is basically making, so, all right, so using this technique of interference, you can make measurements on the scale of the length of laser light, and by using that in the interferometer setup.
I was more interested in the measuring device at the end.
Oh, in the photo multiplier tubes, and that is something that I don't have much expertise in, sadly. They don't let me touch the detector. I can't understand anything. I would create something. Yes?
Yeah, when the gravitational wave passes through the detector, it affects the dimension of space-time and with it, wherever the Earth and instrument is located. It is not also affecting the wavelength of light.
So it does affect the wavelength of light, but it doesn't affect the number of peaks that are detected coming out of the detector as a function of time. And so by measuring not specifically the wavelength of light, but the number of cycles of light that come out, we can actually separate the general relativistic stretching and squeezing of space-time from the signal we're looking for.
But that's the number of peaks.
Yes.
Don't are related to the wavelength?
Yeah, but because time and space are both being manipulated, it's not quite the same effect on the number of peaks coming out as the effect on the wavelength itself.
That you have to understand.
Yeah, it gets very very deep into general relativistic concepts that our founder Kip Thorne has very solid understanding of, but it doesn't quite trickle down to all the ranks. Yes.
Four-dimensional space-time must be very turbulent with all of the gravitational waves produced by many, many things.
Yes.
It must be very difficult to discriminate a single source.
So for LIGO, we are fortunate and unfortunate in our noise sources. So the seismic activity on the ground and all of the details of the interferometer setup make a noise floor that drowns out most of that turbulence and gravitational radiation that you're talking about. So we don't have the problem of having to disentangle all these very quiet sources that make this kind of gravitational wave background. And we only see the very, very, very strong emissions from these compact binary mergers locally on Earth. When we go to space, that is a very different problem. Then you see very much of the turbulence in the local environment from gravitational radiation from white dwarfs in the Milky Way galaxy are the strongest, that make this really, really turbulent, noisy background. And in terms of the white dwarf binaries, we can't disentangle any one source of those because it's just a huge population in the Milky Way that all add together to just give this kind of Gaussian noise in gravitational waves. But they hope that very, very strong emissions in space will be detectable from supermassive black holes merging. So galaxies colliding and having their supermassive black holes collide. And then the amplitude of those signals sits way, way above this turbulence and gravitational radiation from all of the local sources in our galaxy, we hope. But we need to go to space to find out. Yes?
Will detecting gravitational waves tell us something basic about the universe?
So there are two very different camps. One that thinks gravitational waves are still very much a theory, and that they think that opposing theories of how gravity works could rule out gravitational radiation. By far the majority of the astrophysics community feel pretty certain that gravitational waves exist. And things like the Taylor Pulsar give us indirect evidence that gravitational radiation is being emitted from these binaries. But it will be likely, if we reach 2019 and 2022 without detecting gravitational waves from any sources, then it's likely that the formation mechanisms for sources that we expect to emit gravitational waves will suffer the most. And I think theorists have enough room wiggle how often these things form and merge, that are believable, that those are ruled out before the actual generation of gravitational waves is ruled out. Yes?
So I have a question that's really basic to try to understand how to think about these gravitational waves. And I asked it last week of Dr. McCann, and he said he didn't think it was a bad question and tried to answer it.
Okay.
I hope I'm being fair to him by saying I got the impression he didn't think he was the best person to answer it. So
Okay.
I'm going to try again.
Okay.
So if we have these models these graphics that you put up typically with the graph paper type lines around the mass, and we think of them as a sort of imaginary line that defines where light will travel. If we're not to remain within the realm of the imaginary and to get into something real in space, it seems to me, in my naive thinking, that it should be identifiable with some feature of space that moves or gets pushed from one place to another relative to something else. And what is it that is this feature of space that seems to move like a pudding that gets pushed out of the way of mass?
Okay, so I'm not sure I understand the question completely, but do you picture space and time as having a kind of medium, a fluid that gets pushed around by the existence of curvature? But do you feel like there should be something tangible that's actually getting curved by
this
the
would be a mechanical type model, and your lines are just imaginary lines. They're systems of numbers, and I'm trying to figure out how they relate.
Okay.
If there is something real about space and time that makes these imaginary lines get displaced, that it seems to me that it ought to be articulable what it is. I don't understand what it is.
Okay. All right. I think I need to think more about this. So maybe we should talk over lunch. I'd like to talk more about it. See if I can answer your question. Any other questions? Yes.
With respect to gravity waves, are you viewing them in the same terms as photons, in other words, gravitons, or is there a different concept involved here?
I think just like photons, you can think of them either as waves or particles, depending on what measurements you want to make. We very much think of gravitational waves just in the wave aspect and not in the graviton particle aspect, because we are measuring the change in frequency specifically. The gravitational waves that I showed from a compact binary change in frequency as a function of time as they go past the Earth. And that's all of that is rich in detail that we really want to measure. So I think in our minds it's just easier to think of them as waves as opposed to particles with changing energies.
Thank you. The other aspect of this is, as the frequency drops, or I should say gets longer, the energy involved also drops.
Right.
So that extremely distant objects may be giving you an extremely low signal-to-noise ratio.
That's right.
How do you compensate for that?
So we can't really compensate for it. We just have to operate within the confines of the detectors we have. So if they're too far away or the frequencies are too low, then we just can't detect them. And so when the waveforms that I showed were the last few seconds of the whole merger of this compact binary system. In reality, these things have been spiraling toward one another for hundreds of millions of years. And we haven't been sensitive to their gravitational radiation up until the final few seconds because the wavelengths are so long and the amplitude is so weak. So we really only have this very, very narrow window that we can see these things in, and that's where we have to learn as much as we can from an individual source.
Thank you.
Yes?
Yeah, last week, the speaker told us that don't take the rotation speed of these bodies that they're creating, these gravitational waves, as determining the wavelength of these. And the wavelength could be light year. And I didn't understand what is the mechanism that
So I don't think I can describe it so you're asking what the mechanism is for turning fast rotation of a body into gravitational radiation?
Into a long wave.
Into long.
A light year long.
Yeah. So the equations actually change a lot depending on where in the system, where with respect to the source you're looking at the gravitational radiation. We have what they call the near field gravitational radiation, and if you're basically within the source of the gravitational wave. So, for example, assume we could measure the gravitational waves emitted by the Sun-Jupiter system. We're in the middle of that source, and the ripples in spacetime do not look like this very clean sine wave type of gravitational wave that I've been showing, and it's a much more complicated picture that I don't even know if we can solve in terms of the equations. And so it's only from very, very far away that this whole picture is actually real. And so we need to be very, very far from these systems to measure these very long wavelengths. So it's hard to tie it intuitively to the exact dynamics that are happening very, very close to